Hi, this video is going to be about chemical equations, balancing chemical equations, and types of different chemical reactions. So we'll start off with chemical equations. There have been many equations that you've seen, many equations you've written, equations I've talked about, but I haven't been specific about what constitutes a chemical equation. So if I have a chemical equation, some chemical reaction has occurred, and so we have reactants, which are the things that I'm starting with, and we have products, which are the things that I end with. We need to include the states of those substances, meaning solid, liquid, gas, or aqueous, and we need to balance the equations, and this is called obeying the law of conservation of matter, meaning if I start off with 5 carbons, when I'm finished, my reactants must have accounted for all 5 of those carbons. I can't have more carbons than I started with or less carbons than I started with, but we'll get specific about that in a minute. There's going to be an arrow that separates my reactants from my products, and over that arrow or below that arrow, there could be an environmental condition, such as, it might say platinum, and so that could be a platinum catalyst, or it might say 180 degrees Celsius, or it might say UV for UV light causes this reaction to occur. And then the last one, heat could be used, shown as a reactant or a product, and that is shown with a delta, which is a triangle. So the capital delta letter is a triangle. All right, so the states that we're going to have are going to be gas, and we're going to write that parentheses lowercase g, solid parentheses lowercase s, liquid parentheses lowercase l, and it's L, not a 1 or anything like that. We need to make sure that we're using serifed fonts like Courier New. And the last one is aqueous. So this can only happen if I've got something that has dissolved in water and the water has dissolved it, made it aqueous. So here's an example of a chemical reaction. This is methane being burned, methane gas being burned with oxygen to produce carbon dioxide and water. So we've got our reactants, and then we've got our products, and I've got states for everybody. I've got an arrow. I don't have any conditions here associated with my arrow. We could put a delta T here because this is the combustion of methane gas, so heat can be produced on the other side. I have not balanced it. So that's our next topic. So the problem with this chemical reaction that I have right now is there's 1 carbon atom here and 1 carbon atom here. That's awesome. There are 4 hydrogens, but there are only 2 hydrogens over here. So I am not balanced. Another problem with this is there are 2 oxygens that I started with, and I have 3 oxygens that I ended with. So this is not a possibility. This reaction is shown in an unbalanced state. The reaction can still occur if I have more of these substances. So this balancing of the equation, the other term for this is called stoichiometry. So what we need to do is we need to make sure that the exact same number of atoms are on both sides. So let me get myself some space here. Sorry, there's the cursor. There it is. Give myself a little. There we go. So let's balance this methane reaction. So what we have here is 1 CH4 and then 1 CO2. So tips for balancing chemical equations is I tend to wait to do oxygen till the end because it's usually in more than one substance of the products. So what you end up with is you change one thing and you end up changing. I change something over here, and then that makes me change something over here, which makes me change something over here, which makes me change something here, which makes me change this again, which makes me change this one, and then you kind of get caught in a loop. So just do oxygen last. Another tip would be anything that's by itself, like an element just written, like if you see something like sodium, solid, do that one last, because it doesn't have another component to it that you might mess up, like if it was NaF. Now there's 2 things in that that substance instead of just 1. All right. So, like we said, we don't have my hydrogens balanced. So the way I'm going to balance that is I will end up making 2 water molecules. Sorry. 2 water molecules. And now you can see that there are 4 hydrogens here to go along with the 4 hydrogens that I started with. I also added an extra oxygen to this. All right, so now let's count things to make sure we've got everything set correctly. So I've got 1 carbon and 1 carbon, so that's good. We already said we've got 4 hydrogens and we've got 4 hydrogens. Okay, so that's great. Now we've got 2 oxygens, and here we've got 2, 3, 4 oxygens. So I made oxygen? That's not possible. So what I end up needing to do is if I put a 2 here, so let me erase everything else and see what we've got. So this was an H2O. So I'm going to combine these like terms. I'll just leave it as it was. Okay, so 1 methane, 2 O2s makes a CO2 and 2 water molecules. So we could write it CH4 plus O2 plus O2 yields CO2 plus H2O plus H2O. But I mean, it's not that bad here, but what happens if I have 5 waters? I don't want to keep writing that, or 25 waters. I don't want to write it like that. So what we do is we combine these like terms. So we end up removing the other one, and I'm just going to put a 2 here. So this means this, 2 separate oxygens. And this means this, 2 separate water molecules. It's just I've condensed it. Okay. So this is now a balanced chemical equation. 1 carbon, 1 carbon. 4 hydrogens, 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 oxygens. 1, 2, 3, 4 oxygens. That's it. So we can give some other examples of balancing. So this is glucose, oxygen, carbon dioxide, and water. This is what you're doing right now. This is cellular respiration. You can see that we've got 6 oxygens and another 2 oxygens. So there's 8 oxygens. Over here, I've got 2 and 1, so that's only 3. So I don't have enough. So I need to balance this out. So I can see that I've got 6 carbons here. So I'm going to put a 6 in front of the CO2. So when you take glucose and you react it with oxygen, you will make 6 carbon dioxide molecules, and each one of those has 1 carbon in it. So that takes care of the 6 carbons that are in the glucose molecule. All right. You've got 12 hydrogens. So if I put a 6 here, that's 6 water molecules. And since each water molecule has 2 hydrogens in it, that makes a total of 12 hydrogens. Okay, so I've balanced out my hydrogens and I've balanced out my carbons. Now let's balance out our oxygens. So I have 6, 7, 8 total. Over here, I've got 12 and 6. So 12 and 6 oxygens. So I've got 18 oxygens I need to deal with. Alrighty, so I can take care of that. There's 6 of the oxygens right there. So that means I have 12 more oxygens to deal with. And if I put a 6 in front, then I've got 6 oxygens making 6 O2s making 12. And so you can see that I've written the chemical formula as it should be written right here. That's it. Wrote the methane gas one here. I wrote the methane gas one as these 2 O2s and these 2 H2Os. That's what it means. And then I have another example down here. So I will give you lots of practice for balancing chemical equations, but that's really all there is to it. Most of it is just trial and error. If everything is balanced and you just guessed and got the numbers right, well, good for you. That's all that really matters. So if I'm looking at this chemical reaction here, just to be super clear about this, if you take 1 methane molecule, a CH4, you must combine it with 2 separate O2 molecules. And when you do that, you will make 1 carbon dioxide molecule and 2 separate water molecules will be made. That's how this functions. So we reduce that down to 2O2 and 2H2O. All right, there's a good balancing chemical equations, well, a couple of good balancing chemical equations worksheets on Moodle under worksheets, and there are a ton of them in the book. All right, the last thing we'll talk about with this video is types of chemical reaction. So we'll talk about 5 types and then then a subtype. So the 5 types are decomposition, combination, single replacement, double replacement, and combustion. So a decomposition reaction is where one thing becomes 2 things or more things, 2 or more things. A combination reaction is 2 or more things turn into one thing. A single replacement is I have something by itself, and then I've got a binary compound, a compound composed of 2 things. And the thing that's by itself replaces one of the things. And now that thing that used to be in a compound has been kicked out and it's by itself. And then I have a new binary compound. And then the double replacement reaction, basically, each one of the binary compounds, they swap partners. So it was ABCD, now it's ADCB. And then the last one, anytime I have some substance, doesn't matter what this substance is, and I combine it with oxygen, I will make a new substance that is that thing plus oxygen and possibly some other stuff. So we can see that right up here. This is a combustion reaction. This is methane being combusted with oxygen. The carbon and the oxygen go together to make this CO2 and some other substance. And so that's why we have a combustion reaction, because the O2 is combusting, in this case, methane. When we think about combustion, there's a fire triangle. I don't know if you remember this from like 4th grade. Fire department came out, heat, oxygen, and fuel. So if you take one of these things away, you can get the fire to go out. It needs all 3 of those. All right, so I've got some examples of these different types of reactions. So here's a decomposition reaction. This is ammonium nitrate, and the ammonium nitrate turns into nitrogen gas, hydrogen gas, and oxygen gas. So one thing turned into multiple things. Then I have a combination reaction. This P4O2 turns into P4O10. It's these reactions, this particular reaction is not balanced. The first one, I did balance that one. So to balance this one here, I would need a 5 in front of the oxygen. And then that would give me 5 oxygens on the left and 10 oxygens on the left and 10 oxygens on the right. The next one is a single replacement reaction. I've got this zinc atom sitting by itself, and it goes in and it kicks out the copper ion, and the copper turns into copper metal or copper atom. And then I get a zinc ion that is now combined with chloride. The double replacement reaction, I have table salt and I have silver nitrate. And when I'm finished, I have silver chloride and I have sodium nitrate. So the Na and the Ag swapped partners. And then I've got, this is propane gas with some oxygen. So it's being burnt. And then I end up with CO2 and water. That's the exact same thing that we got when we burn methane. It's also the exact same thing we got when we have cellular respiration. You take that oxygen and that glucose molecule and you make CO2 and water. So technically you and a car exhaust the exact same thing. Your exhaust pipe is your mouth. The car's exhaust pipe is the exhaust pipe. And what comes out of each of you is the same thing, CO2 and water. This one's not balanced. I can balance this one out real quick. 3. So if I put a 3 here, that'll give me 3 carbons on each side. If I put a 4 here, that'll give me 8 oxygens, or sorry, 8 hydrogens on each side. And so here, this gives me 6 oxygens, and this gives me 4 oxygens. So that's 10 oxygens. So if I put a 5 here, then this is balanced. 1 propane with 5 O2s yields 3 CO2s and 4 water molecules. Okay, there is another type of classification for a chemical reaction, and it's called a redox reaction. And redox stands for oxidation and reduction. You've probably heard oxidation before, but possibly not reduction. So when an atom changes its number of electrons, either gains electrons or loses electrons, it's said to be either reduced or oxidized. So anything that is gaining electrons, anything that gains electrons is said to be reduced. Because if I've got, I don't know, a sodium with a plus charge, +1 charge, and it gains an electron, it turns into sodium with 0 charge. So what happens to its charge? Its charge went down, so that's why it's reduced. On the other hand, though, if I've got a sodium atom and it loses an electron, this is said to be oxidized. So reduced is reducing the charge, becoming more negative because I'm gaining electrons, and oxidized means it's becoming more positive because it's losing electrons. The reason the word oxidized is used is because when chemists were first studying this, the thing that constantly took electrons away was oxygen. And the reason that is the case is because oxygen is all over the place. It's in the atmosphere, it's readily available. And oxygen is the second best element at taking electrons away, fluorine being the most capable of taking electrons. If there was fluorine in the atmosphere, we'd be calling this fluoridation instead of oxidation. You've probably actually heard the term fluoridation, which is adding fluoride to water, and that kills bacteria and also makes the water taste super bad. But and it also helps with tooth decay, increasing the strength of the enamel on your teeth. So it's not just bad tasting water. So how do I know if a particular chemical reaction is an oxidate is a redox reaction? Well, let's look at some of these guys up here. Any atom that's in a molecule has a charge. So all of these atoms have charges. The nitrogen, hydrogen, and oxygen are charged. We don't even need to know what their charges are in this case. On the other side, this is nitrogen in its elemental state, so its oxidation state is 0. This is hydrogen in its elemental state, so its oxidation is 0. This is oxygen in its elemental state, so its oxidation is 0. So all three of these have oxidation states of 0, and all the atoms on that side don't. So that had to be a redox reaction. Some of those atoms gained electrons, some of those atoms lost electrons, but regardless, that's what we end up with. This is an element in its elemental stage, this phosphorus. So its charge is 0. This is oxygen. Its charge is 0. Over here, it's not 0. So I know a redox reaction occurred. This is zinc. This is metal zinc. So its charge is 0. This is zinc inside of a compound. So its charge is not 0. So I know this is also a redox reaction. And the other way I can look at that is this is copper. Its charge is 0. Inside this compound, its charge was not 0. So we had a redox reaction occur there. Actually, the only one up here that isn't a redox reaction is this double replacement. These guys just swap partners. Nobody changes any electrons. So the double replacement reaction is never a redox reaction. And then we can use that same logic down here. Oxygen's charge is 0, and over here it's not 0, and over here it's not 0. So that means the oxygen has had its number of electrons change. The last thing with this is a little side note with reduced and oxidized. There's another way to refer to these things as reducing agents and oxidizing agents. So if I'm iron and I encounter oxygen, I will lose electrons and become +3, and oxygen will gain electrons and become -2, and we'll end up with rust. So this oxygen oxidized the iron. How do I know it oxidized? Because it was 0 and it went up to +3. So that means oxygen gas is an oxidizing agent because it was able to oxidize the iron. Then the other way to think about it is, what did the iron do to the oxygen? Well, the oxygen's charge was 0 and now it's -2. So the oxygen was reduced. So this is iron is a reducing agent. Iron was actually able to make oxygen's charge go from 0 to -2. So its charge went down. And this is interesting because this is oxidizing agents. That's what's in OxyClean. Usually use some form of peroxide, but the peroxide ends up taking electrons away from stuff. And when stuff loses electrons, it usually loses color. So if you've got a tomato stain on a t-shirt and you put it in the washing machine with OxiClean, the OxiClean will probably not be able to get the all of tomato sauce off of the shirt, but it can make what's still stuck to the shirt not visible. So it removes electrons in a way that makes it so it does not show color anymore in the visible spectrum. You can check that by using a black light, and it will probably glow. That happened to me once when I had a really favorite white t-shirt that I just kept bleaching every time I got something on it. And then we went to a restaurant that had a black light as you walked in, and my shirt looked like it was camo because there were so many spots that I had oxidized out. Okay, that is all I have for this set of discussions about chemical equations, about balancing chemical equations, and about different types of chemical equations.